Hi, I'm Kathy. In this lesson, we're going to look at different sets of numbers and do some problem solving. Our specific objectives are sets of numbers, scientific notation, and problem solving. Let's start with sets of numbers. The first two sets we want to be clear about are the natural numbers. These numbers are the counting numbers, 1, 2, 3, 4, 5, etc. A set similar to them are the integers. These numbers are the positive and negative natural numbers, as well as the number 0. So here are the natural numbers, here are the negative natural numbers, and the number 0. Here's another set you need to be familiar with, the rational numbers. Any number that can be expressed as the ratio of two integers, p over q, where q is not 0, is a rational number, and here are some examples of rational numbers. Notice that any integer, and therefore any natural number, is a rational number, and a fraction where the numerator and denominator are integers, like the next two examples, a decimal that terminates, which means stops, a square root or a root that has an exact value, and a repeating decimal. We'll compare that set to the next set, which is called the irrational numbers. These numbers include all non-terminating, that means non-ending, and non-repeating decimals. And finally, we get to the real numbers. These numbers are or include both rational and irrational numbers. And irrational numbers, again, are non-repeating and non-terminating decimals. Here's some examples of real numbers. In here you'll see an integer, it's a real number. You'll see pi, that's an irrational number, a non-terminating and non-repeating decimal. A square root of any number that doesn't have an exact square root. 4/3 is a real number that is rational, as well as 0, negative 13.8. Well, let's look at an example involving some numbers. Here's what we want to do, or what we're given. The following table lists the Consumer Price Index, called the CPI, for selected years from 1950 to 1995. As an example, a CPI of 24.1 indicates that a typical sample of consumer goods costing $100 in the years 82 to 84 would have cost $24.10 in 1950. Well, here's the table. Let's just investigate it or analyze it just a little bit. Notice the 24.1 is the CPI for 1950, and the years 82 to 84 are not in the table, but 100 would have fallen between 82.4 and 107.6. So just examining the table a little further, something that costs $100 in the years 82 to 84 costs $153.50 in 1995. That's what the table data represents. Here's what we want to do, or the first thing that we want to do. We want to approximate the percent change in prices from 1970 to 1980. Well, in 1970, the CPI was 38.8. In 1980, the CPI was 82.4. I have that information written down on a sheet of paper. 1970, 38.8. 1980, 82.4. To calculate the percent change in CPI, in prices, what we're going to do is take one of the CPI values minus another divided by the first. I've written C2 minus C1 divided by C1. We want to have a positive percent change because prices have increased. So for this particular problem, we'll take 82.4, subtract 38.8, and divide the result by 38.8. When we're done doing that, we'll multiply our answer by 100. Now if you do this subtraction either by hand or on a calculator, you'll get 43.6, still divided by 38.8 times 100. And doing that division, we get approximately 1.12, which times 100 is the number 112. That's the percent increase from 1970 to 1980. Well, let's continue with this example, but do another problem. From 1980 to 1990, the average tuition and fees at public colleges and universities rose from $804 to $1,908. Do Determine if the percent change in tuition and fees was more or less than the percent change in the CPI for the same time period. So you'll need to look back at the table for the CPI values from 1980 and 1990, and I've written them on a separate sheet of paper. The CPI value in 1980 from that table we started with was 82.4. From 1990 is 130.7. Let's find this percent change first, and then we'll compare it to the percent change in tuition. So using the formula, we have 130.7 minus 82.4 divided by 82.4, and then we multiply by 100 to make that a percent. If you do this subtraction, this comes out to 48.3 divided by 82.4, and dividing there, that's about 0.59, which times 100 says prices increased 59% over this 10-year period. Well, let's compare that to the change in tuition. Doing the same calculation, or similar calculation, different numbers, 1,908 minus 804 divided by 804 times 100 is, again, subtract on a calculator or on a piece of scratch paper, 1,104 divided by 804 times 100 is about 1.37 times 100, which is 137%. Notice that tuition and fees far outpaced the CPI for that time period. Let's move on and talk about scientific notation, starting with the definition. Scientific notation. A real number r is in scientific notation when r is written as c times 10 to the n, where c is a number greater than or equal to 1 but strictly less than 10, and n is an integer. Let's look at some examples. Here what we want to do is complete the table. We're given numbers that are in standard form in scientific notation. In the first example, we have the number 45,000. That's the number 4.5 times 10 to the fourth. Notice that 4.5 is between 1 and 10, and 4 is an integer. And if we were to translate the scientific notation back to standard form, we would take this decimal point and move it 4 places in the positive direction. In the next example, we have the number 0.0000567. Let's see, that's 1, 2, 3, 4, 5 places that the decimal would need to move to get 5.67, a number between 1 and 10. But notice that the exponent on 10 is negative 5, because in order to change this number back to standard form, I need to move the decimal point in the negative direction. Well, let's fill out the rest of the table. Here we have 5,300,000,000. We want to write the first part of the scientific notation as 5.3. So we have a number between 1 and 10. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places needed. So we write 10 to the positive 9th because the decimal point would have to move in the positive direction to get the standard form. Now the next number is itself a negative number, so we need to write the first part of our scientific notation as a negative number. The significant digits here form the number 9.8, and the power of 10 we want in our scientific notation 1, 2, 3, 4, but negative, because that decimal point will have to move in the negative direction to get the number in standard form. Now let's go the other way. Here we have scientific notation and we want standard form. Notice that our number will be negative, and we'll have to move this decimal point 4 places in the positive direction. That gives us 7800, adding enough zeros to get 4 decimal places, or negative 67,800. In our last example here, we have 2.11 times 10 to the negative 3. That means the decimal point needs to move 3 places in the negative direction. If you consider moving 3 in the negative direction, we'll have to put 2 zeros to the left of the 2 to get the correct standard form. Well, let's continue with scientific notation, but do some calculations with it. Here's what we want to do. First thing we want to do is find 3 times 10 squared divided by negative 4.5 times 10 to the negative 4th, all of that times 6.8 times 10 to the 7th. Here's a good time to pick up a calculator. At home screen on our calculator, we're going to enter each number as it is, and there's a key on your keypad that has a double E behind it. It's actually on the keypad. We'll use that when we're ready to put in scientific notation. The first piece of our first example here is a division, and so I'm going to use parentheses to enclose the division, but a second set of parentheses to enclose the numerator, 3 second double E, which gives me 1 E on the screen, which is the calculator's version of times 10 to the. Now next to that, only put the exponent from the 10 in the scientific notation. Closing the parentheses, that's the number in the numerator, and I want to divide that by, using parentheses, the number negative 4.5, and again I choose the double capital E button, which means times 10 to the, and next to that put the exponent on 10, which is negative 4. Now I'll close parentheses for the number in the denominator, and I'll close again for the fraction that was division. Now I want to multiply that, continuing, times 6.8 times 10 to the 7th. You can put a times symbol or another set of parentheses, whatever you're comfortable using. 6.8 second E, or EE, and then a 7 for the power of 10. Now when you push the enter button on the calculator, it does a calculation, and it tells you the result is negative 4.533333 E13. Now as we write that number down, we're not going to write an E on our paper. We're going to understand that E13 means times 10 to the 13th. In addition, I'll round to a couple of decimal places as I write this solution down. So the answer to the first calculation, negative 4.53 times 10 to the 13th. Well, let's try this next calculation. Here we see the square root of 987,600. That result times the difference, 2,387 minus 7,654,000. Well, let's put that in as we see it on our calculator. So we'll start with a square root. Remember, that's down the left column. And the number in our square root is 987,600, 987,600. Don't forget to close parentheses to just enclose that number in the square root. Now I want to multiply that by 2,387 minus, be careful that you use the minus, not the negative key. Let's see, 7,654,000. Now I'm going to push the enter button, and I get negative 7,604,025,016. Well, let's translate that to our paper and then think about how to write that in scientific notation. So our result here is negative 7,604,025,016. Well, we know how to write a number from standard form into scientific notation. And this one, I'm going to round to 2 digits, but it's a negative number. So I'm going to call it negative 7.6 times 10 to some power. Let's count the decimal places. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's approximately negative 7.6 times 10 to the 9th. Well, now it's your turn to try a problem like these. I'd like you to stop the tape and work the following problem, and when you're done, restart the tape to check your work. Here's the problem I want you to try. I want you to use a calculator to approximate the expression negative 9.8 times 10 to the negative fifth times 3.4 times 10 to the ninth divided by 4.57 times 10 to the fourth. Give this a try. Well, let's see how you did. We'll definitely use a calculator to help with this. What we want to find on our calculator is, first with parentheses, negative 9.8 times 10 to the negative fifth. So using our scientific notation on the calculator, putting in negative 5, then I have that times 3.4 times 10 to the ninth, and that's the whole numerator. I probably should enclose my numerator in parentheses. So let me go insert a set of parentheses, and I want a second close parentheses. Then I want to divide that by the number 4.57 times 10 to the fourth. Checking that over, looks okay. Let's push enter, and we get a number that's not in scientific notation, negative 7.2910. We could write that. Let's write the result on our problem sheet here. If we round to 2 decimal places, that's the number negative 7.29 once rounded. If you wish to write it in scientific notation, you could write it times 10 to the 0 power. Well, let's finish this lesson with a problem and do some problem solving. Here's what we're going to do. For some jobs, employees are paid time and a half for every hour worked over 40 hours and double time for all hours on Sunday. Suppose an employee's regular hourly pay is $12. Find the pay for 47 hours from Monday through Saturday and 8 hours on Sunday. So as I read the problem, there are 3 pieces we need to calculate. We need to calculate the employee's regular pay, their sort of regular overtime pay, that's through Saturday, and then their Sunday pay. Well, if you look back at the problem, the employee worked their regular 40-hour work week and earned $12 an hour. As far as the regular work week through Saturday, it says in the problem the employee worked 47 hours. So that's 7 extra hours at time and a half. So let me multiply that by 1.5 times the $12 per hour. So here's my time and a half. And then the employee worked 8 hours on Sunday, and that's double time, so I'll use a 2 times the regular pay of $12. Well, what we need to do is get these 3 values, sum them together, and that's the employee's pay for the week. Well, this one I can do in my head without too much difficulty. That's $480. Let's turn to a calculator to do the next one, just so we don't make an error. We want to do 7 times 1.5 times 12. And while we're here, we'll do our other calculation, 8 times 2 times 12. So we need to include $126 and $192. Let's write those down. 126 and 192. Now the sum of these, 480 plus 126 plus 192, is the pay for the week, which I think comes out to $798 for the week. Well, in this lesson, we've looked at different sets of numbers and done a little bit of problem solving. Be sure to practice by working lots of exercises from your textbook.